So 6.1 is the introduction to two variable equations. So all of chapter 6 is all about graphing and graphing linear equations, and two variable equations are linear equations. And so we're going to take some time with these two variable equations and understand a little bit more about them, because they're going to be the topic of study for chapter 6, 7, and 8 in this course. And so when we talk about a two variable equation, we've moved up in the number of letters that we're going to be capable of solving equations with, but down in the term of exponents. And so the standard form of any linear equation has two different variables in it, but there are no exponents in that equation. And so linear equations have two variables. And if we were to take a linear equation, it's called a linear equation because it literally makes a line. So going back to that 6.2 coordinate plane that we were talking about, if I were to take and draw any straight line on this, and so I'm terrible at drawing straight lines. Oh, that's not too bad. There's a straight line. We could come up with ordered pairs that make up this line. So that could be maybe 1, 1. Maybe this is 2, 2, right? All along here, every point on the line has a reference, has instructions on how to get there, has an address of an ordered pair. So for every linear equation, for every line, there's an infinite number of solutions. This line goes on in both directions here forever. And so there's an infinite number of ordered pairs that fall on that line. So that's why it says here, solutions to linear equations are ordered pairs. So we know that they are x, comma, y, right? That's the value of x, that's the value of y of these locations. And the values of x and y satisfy or make the equation, this is an equation, make the equation true. So it says here solutions are ordered pairs, and a solution makes the equation true. The ordered pairs, as we know, are written as x, y, where x is on the horizontal axis and y is on the vertical axis. This kind of stuff, understanding this and my picture up here is why I did the 6.2 first, because it gives you some context of sort of the map of the world here, or the layout of where we're going with these things. So we're going to monkey around here with some linear equations. The first thing we're going to do with the linear equations is we are given a linear equation and basically said, hey, if there's an infinite number of solutions, what about these ones? Is this a solution? Or is this a solution? Or is this a solution? And what we're meant to do here is say, well, as an ordered pair, that means that x equals 2 and y equals 5. So what we're going to do is verify or check. You remember when we've done this before. If I have left side and right side of the equation, I'm going to take and evaluate the left-hand side, subbing in the 2 where I see the x and the 5 where I see the y. It's always a good idea to sub in with brackets, but sometimes it's not necessary. In this case, we get 4 plus 5, or evaluate that as 9. Now the right-hand side of my linear equation, going back to the original, said it was 9. And because my left side and right side are equal to each other, that means that that solution, this 2, 5, is a solution for this linear equation. It checks out. Again, if we've got another ordered pair to verify, the 5 would be representing the x variable and the negative 1 would be representing the y variable. So to check if this is a solution to this linear equation, I'm going to set up this left side, right side verification thing, and I'm going to rewrite the equation subbing a 5 in where I see an x and a negative 1 in where I see a y. That gives me a 10 minus 1, and it gives me a 9. And the right-hand side of the equation was a 9. So again, that's another ordered pair that fits as a solution for this linear equation. One more to do here. Again, the 3 is representing the x, the 4 is representing the y, and so to verify this solution, I check it out, left side, right side. I sub in the values that are potentially correct, and I evaluate them to see if things actually add up and check out. And in this case, because the left side and the right side don't check out, that means that this point is not on this line. This is not a solution to this linear equation. So we've got b down here, and this is one you can do for yourself. We have a new linear equation to deal with. And we have potential answers. So again, what you're doing with this is like we did at the top. You're checking it out. If you sub in and evaluate the x and y values, does it satisfy this equation? Does it make it happy? Does it make it true? And so you're going to be able to check all three of these to determine if they are actually answers for this linear equation. So you can take your time to do that. I'm going to throw up the spoiler here. But take your time. Subbing in with brackets is always a good idea. You don't have that case of squared terms anymore, but it is still a good habit to be in. So the next section here gives us something else to do with linear equations. So this time we're given a linear equation and part of the solution. So we're given the x value, but we don't know what y is. And so in these ones, what we're supposed to be doing here is subbing in to find the full solution. And in these ones, I think it's a good habit to get into writing your answer as an ordered pair. So what we're going to do is follow the instructions that we're given here. So this one says take x and sub it into the value 5 and figure out what y actually is. So let's take a look what it looks like when I do that. So 5 plus y equaling 5. You could sub in with brackets, but sometimes they're a little redundant. I wouldn't blame you if you didn't. So now we need to solve for y. To get y all by itself, I'd subtract 5 from both sides, and I'd get that y equals 0. So what this is saying is that 5, 0 is an ordered pair that is a solution to this linear equation. And again, if you wanted to check this, you could verify the solution with left side, right side. You know me, I'm not going to go through it, but it should. Check it. Okay, so another one, same thing. So we're dealing with the same linear equation, and it's like a fill in the blank type thing. So this time we want to know what x is, that's our question mark, when we know that y equals 5. So we go back to that original equation. I put x as x because I don't know what it is, plus 4 because that's what y is, and you could sub in with brackets. I would just write them and then erase them, so I've saved myself that time. And solving for x, I would subtract 4 on both sides. So I get that x equals 1, and x equals 1 when y equals 4. And so what I'm saying here is that this ordered pair, 1, 4, is a solution for this linear equation. It is a point on the line that is defined by this equation. Couple more to try. You can give these ones a go. What we're trying to do here is sub in and figure out what y is when x equals 4. So I sub in 4 for x, and now I can solve for y. Going the distance, it's the same mechanics of solving like we did back in chapter 2. We know more exponents. And again with this one, I should give my answer as an ordered pair. I put the box around y equals 6 because it does, but my ordered pair would be 4 and 6. That is the full solution to this linear equation. Okay, one more. I love subbing in zeros, as you will soon hear. So x is what I don't know, but I do know that y equals 0. When something times 0 is in there, I just write it like that. It's just 0, so I can just get past that. 2x equaling 26. And solving for x, I get that x equals a 13. So again, writing it as an ordered pair, because it's a nice, neat way of representing all the information. This is a solution to this linear equation. One more way to look at this, you're doing the exact same thing, especially since I've been reinforcing ordered pairs and the way of writing ordered pairs, that notation style. So what this one is saying now is you've got 4 questions to do with this one linear equation. And in each case, you have part of a solution. So this is telling you, figure out what y equals when x equals 9. And so what we do with this one is sub a 9 in where I see the x, and then solve for y. So I get a final answer of y equaling 1. And again, with this one, you don't have to rewrite it as an ordered pair. You can just fill in the blank there because that's how the question was given to you. So 9 and 1 is an ordered pair that would be on this line. It is a solution to this linear equation. Doing the next one here, these aren't really complicated. They're just a different way of writing things, really. So this one's saying, what is x? That's our question mark when y equals -1. So it'd be 3 minus, or sorry, I'll just write, not talk. So that's it with the y subbed in. And then solving for x, I get that x equals 3. So I can fill my answer in the ordered pair that was representing really the question here. Last two, I really love subbing in zeros, usually because it's quick. So what I'm saying is solve for y when x equals 0. So I sub in 0 where I see that x, and then I'm going to solve for y. Well, that's just nothing. It's not there. So I get a final answer that y equals a -2. And again, I'm filling in the blank in my ordered pair with this. Last one, this time it's the y equaling 0, and we don't know what the x equals. That's what we're trying to figure out. So when I sub in, I rewrite my equation with the 0 in the place of the y, and now I can solve for x. This one's really quick to do. All of that just wipes out. -3 times 0 is 0. And so x just equals 6 in this case. And so again, filling in my ordered pair, I get 6 and 0 as a point on that line or as a solution to this linear equation. And you could do, like we had said, an infinite number of these ordered pairs. There's 4 more on the next page for you to give a try to. Maybe I'll just throw the answers up, and in class we can take our time working through them. These ones over here, you don't actually have to do both of them. Once you get one, they're kind of redundant. But give those ones a try and give them a check. So to this point, we've been given an answer and asked to say, check it. Is it actually an answer? We've been given parts of an answer and been asked to complete the answer, complete the ordered pair or the solution. Now it's wide open. Now we're going to be given a linear equation and be asked to just find 3 solutions for this. And so what we're going to do with this is a couple things. The first thing we're going to do is, whoops, I've changed color. We're going to solve for y, just algebraically. I'm going to put algebraic like. And then the next thing we're going to do is make a table where you have your x values in one column and your y values in the other. And what you can do here is, with your x's, you get to choose these. You get to choose 3 x values, and you can choose anything you like. Then after we choose that x, we're going to do like what we were doing. You're going to solve for the y values. And so in these ones, there are a few little wrinkles along the way. There are ways of choosing numbers that are easier than others, but this kind of a table is going to produce a list of values that are ordered pairs that are solutions to these. So let's try it with A. The first thing we're going to do with A is solve the equation for y. And so when I take a look at A, I want to get y all by itself. So I'm going to start by getting rid of the x term. I'm going to subtract 2x from both sides. When I do that, I have that y equals. Now, this is a bit of a funny thing. I'm going to teach it this way because I know where it's going. So I'm going to write it as in descending order. We know from our factoring work that that was sometimes important. So I'm going to write it as -2x plus 8. This is something that we're going to come back to in the coming chapters. So I thought it best to just, start off the bat doing things right, because that's going to further establish your habits and patterns when things get a little bit harder. So now that we've got it solved for x, that was the first step. Now we're going to make a table of x values and y values. And I'm going to be able to choose any values of x that I want. And so I like subbing in zeros, as I've already suggested in the examples. I also dislike subbing in negative numbers. I don't know about you, but I make mistakes with negative numbers. So I'm going to pick positive numbers. I'm going to pick the smallest positive numbers possible. You can pick any numbers that you want. You can pick your favorite number. If your favorite number is 18, pick 18. It doesn't matter. When you do questions like this in the homework, the back of the book will say answers may vary, because there literally are an infinite number of solutions that satisfy this linear equation. So now that I have my table set up, what I'm going to do over the side is the rough work. I'm going to take my equation and sub that x value, that 0 in, to evaluate the equation for y. So I get that y equals 8. That negative 2 times 0 just goes away, and so I get 8 for my y value in that first case. This is made an ordered pair, and you could leave it in the table, or you could write it out as an ordered pair. So that's 0 and 8. That's one solution to this linear equation. Moving down the table, what I'm going to do next is take the equation and evaluate it for y when x equals 1, because that's what I've chosen to do. So I'm going to evaluate this and get that y equals negative 2 plus 8, or y equals a 6. So I've completed my second ordered pair here, my second solution for this linear equation. So I could write it out as 1 and 6. The last one, same thing. I'm going to take my linear equation. I'm subbing in the 2 because that's what I've chosen for my x value over here. And solving for the y value, or evaluating it for y, I get that negative 4 plus 8, and y equals 4. And so now I've completed 3 ordered pairs that are solutions to this linear equation. We have another example to do here, and this example has one of these pitfalls in it. So following along, the first thing we're going to do is solve this for y. And so I'd start off by subtracting x in both cases, and that would leave me with negative 3y equaling negative x plus 12. Remember, I said I'm going to write it in descending order because I know how it's going to be useful later on. And we're not done yet. Now we want to get y all by itself, so we divide both sides by negative 3. So now I have it that y equals, I'm going to give us an intermediary step here. When we have a binomial divided by a monomial, we know that we could do that kind of like passing it around kind of thing. So that has to be divided by 3, and that has to be divided by 3. And so I'd get a final equation of y equaling 1/3 x minus 4. So this 1/3 x there, just take a look at that for a minute. So I like seeing it as a coefficient in front of the x term. We know that we have a negative divided by a negative, so that would make it a positive, right? And I could see that as a 1 on the top there. So shifting from the way I had written it up here down to the way that it is in my linear equation is a bit of a trick. But I think that if you get into the habit of this now, it's going to pave the way for where we're going later. So in solving this for y, this allows me to be smarter with my choices for my x values. And so I'm going to make a table. I'm going to make an x, y table. And I'm able to pick any values of x that I want. I am not going to pick negative numbers. I'm going to pick a 0. And now, what else could I do about picking numbers for x that would make my life a whole lot easier? If I were to pick multiples of 3, that's going to leave me in whole number territory. If I could pick 1, but I've worked this out in advance, my answer ends up being negative 11/3. Putting negative 11/3 on a graph is a nightmare. So if I want to stay in whole number territory, I have to choose wisely here. So when you have a fraction as a coefficient on your x, I'm just going to put the notes in another little color here. So with fractions, as coefficients on the x, the key thing here, choose multiples, multiples of the denominator. So what I'm going to do is choose a 3 and choose a 6. Those are multiples of my denominator. So let's see how this works. What we're going to do is sub in the value of x that I've chosen and evaluate this for y. So anything times 0 just goes away and I get that y equals a -4. That's my first ordered pair. You can list it out like I did in this one, or you could even just leave it in the table. I could just read it out of the table as an ordered pair. The next one is a little bit tricky. I'm just going to give myself a wee bit more space on the page here. So what I'm doing now is taking and subbing a 3 in where I see the x. So focusing in on the fraction math here, I'd have 3 over 3. Remember that this is over 1, and 3 divided by 3 is 1. So I'd have y equaling 1 minus 4. A bit of fraction math there. My final answer would be that y equals a -3. And so I can fill in my table with that as my y value. Again, what I'm doing with this table is completing my ordered pair. The last one, and maybe I'll do it just here, I've got that y equals 1/3. I've chosen 6 as my value of x, and then completing my equation was a -4. Again, a little bit of fraction math here, but at least it gives you a whole number, so it's worth having chosen carefully. I get that y equals 2, because that's 6 over 3, which reduces to 2, minus 4. So my final answer is that y equals a -2. And so finishing up this chart gives me my third solution to this linear equation. Always in these linear equations, we have some oddballs. And so we've been dealing with linear equations, which are kind of like that first one that I drew for you. So you have your y-axis and your x-axis. I always have a hard time drawing vertical lines on this tablet somehow. And so typically what we're talking about are lines that go off at whatever angle, right? That was kind of like the one that I had started with. Now, you could technically have a vertical line or a horizontal line, and they're kind of the oddballs, if you will. So I'm going to just work this one up a little bit. I've got these examples. So these ordered pairs, it's saying, are going to create a vertical line. So there's my XY coordinate plane, and I'm just going to do a bit of a sketchy graph. If you flip through in the notes, there's a whole lot of lovely graphs all photocopied into the notes for you, but this one's going to be a bit sketchy. So the first point is 3 and 0. The next point that's indicated is 3 and 4, so that'd be 1, 2, 3, 4, so over here, right? Finding those battleship coordinates. The next one is 3 and -1, so that'd be down here, and then 3 and -4. And so this would create a line, same as all the other lines, but a very specific line in that it's a vertical line. And so the equation for this, as much as we've been saying linear equations have 2 variables in them, sometimes the coefficient on one of the variables is a 0. In this case, the coefficient on the y variable is a 0. And so the equation, linear equation, only has one variable for these kind of special case ones. And so the equation for this would be that x equals 3. Because you can see in the ordered pairs, x always equals 3. And it created a vertical line, and it's a bit of an oddball. We're going to do a similar kind of treatment of the other special case here. So this is saying it's going to be a horizontal line. Let's just take those ordered pairs and graph them. So -5 on the, I'll do this 1, 2, 3, 4, 5, super sketchy, and then 2 down. So there's my first point. And then we have -1 and -2 down here, right? And then we have 0 and -2. And then we have 3 and -2. So 1, 2, 3, way out of scale, but hopefully enough, like just to get a sketchy concept of what's going on. So that does actually make a horizontal line, or pretty close to one. So the equation for this line is that y equals a -2. And so we end up with these oddballs through all of the notes through chapters 6 and 7. All of the time, any of the times we get vertical and horizontal lines, or every time we kind of get a new concept with linear equations, I'll give some time to these oddballs, these vertical and horizontal lines. The last part of this 6.1 material are some applications of this stuff. So they're a little bit hokey, kind of can't help but make a little bit of fun of them. The first one is about you if you run a company that makes staplers. Congratulations. Who knew that was your future job? But say that is your future job. We've got this idea that you can create staplers and get $1.80 on every stapler that you sell, but the company that you operate, the factory or whatever, costs $120 to operate. That's barely enough to pay you. So I'm not really sure how this is operating, but let's just go with it. So we're going to say let X be the staplers, or sorry, the number of staplers. And we're going to say let P be the profit. So there is a little bit of modeling here. We've defined our variables, which is always a good place to start. And honestly, in these, it does say up there that these are kind of just a little bit of extra. We can mathematically model a function like this. And so what we're saying is that profit always equals what you make, your revenue, minus the costs that it costs you to do that business. So your revenue would be $1.80 times the number of staplers that you sell. The deriving of this equation I don't think is worth getting stressed out about. It's just an application of one of these linear equations. The other thing here is a minus your cost. Well, it costs you $120 to keep your business open for the day. So this gives us the linear equation that we're going to use in these other two questions. Oops, that's not really a start. Okay, so it says here, what's the profit if you shipped 500 staplers in a day? Lucky you. So your profit would equal 180, drop the 0 there, sorry, times 500 minus 200, so 120. So you can just use your calculator on this one, and it works out to be $780. That's how much you would make if you shipped 500 staplers in a day. I don't know who you're selling 500 staplers to, but good for you, because you're going to make some money that day. The next part of this is still dealing with this same equation. I'm just going to scroll a little bit so you can see this one. This one says, oh no, your rent is due, or you need to pay your mortgage or something, and you need to get $1,500 worth of cash somehow. So that would be your profit. So it says, how many staplers would you need to sell in order to make that much money? So in this one, that would be your profit. So 1,500 would be your profit, and that would equal 1.80 times that number of staplers. Remember, that's what you're looking for, and finishing out the equation. So we're solving this equation now for that other unknown variable. So I'd add 120 to both sides, and I'd get 2,700 equaling 1.80x. Divide both sides by 1.8. This time I left the variable on the right-hand side. I feel like we're probably getting flexible enough in that. It gives me that x equals 900. So that's 900 staplers you have to somehow sell to somebody to make your debt here, to make your $1,500. That is a lot of staplers. So another application, and I think we would all love it if biology was as obedient as this example is going to portray it to be. So we are going to cure cancer in this one. I know, practical applications, right? So we have a patient who has a cancerous tumor, and the weight of the tumor is one of the variables. So W is for weight of the tumor. Just getting, figured out what all these letters are representing. So the weight of the tumor is W and is related to the days, so D, of chemotherapy treatment. So D is the days of treatment. How many? So it gives us, we don't have to mathematically model, we don't have to come up with the equation. It gives us this linear equation. So it says here, find the original weight of the tumor. Well, that would be on day 0. And so what I'm going to do now is solve for W when day equals 0. So it's on day 0. It's the first day. There has been no treatment yet. And so what I would do is write W equals negative 1.6. It's 0, subbing in for D into the original equation, right? Plus 32. Anything times 0 is 0, and I have this habit of just kind of crossing it out. That means that the weight of the tumor is 32. So it's 32 grams initially. It's the original weight. It's before any treatment. It's 32 grams. So this is the truly optimistic part. It says here, determine the number of days of chemotherapy required to cure the cancer. This is awesome. Pretty sure this isn't how it works, but even if it was close, it's definitely optimistic. So this one, what we're going to do is figure out how many days, that would be our question mark, when the weight is reduced to 0. That would mean eliminate the tumor, right? It's gone to a weight of 0. And so I would have, subbing into my equation, that original equation is not on my screen anymore, but the weight being 0 would equal negative 1.60x plus 32. Oh, sorry, D. Why did I switch to an X? D. Right? So now I'm going to solve for D. I'd subtract 32 from both sides. I'd get that negative 32 equals negative 1.60D. And I'd divide by negative 160 on both sides. Not 160, 1.60. Sorry. Anyway, hopefully you're following along. I'd end up that D equals 20 here. And so what that means that in 20 days, the tumor would be completely eradicated. Definitely good news for the patient. So those are linear equations. We'll move on with more linear equations. These are things that are going to stay with us for the next chapters.